This is section 2.1 on limits. The first thing we want to try when presented with a limit is to just simply plug the value in. So on number 1, we have the limit as x approaches 5 of x squared plus 4. So let's try to plug 5 in. We get 5 squared plus 4. We get 25 plus 4. We get 29. So the limit as x approaches 5 of the function x squared plus 4 is simply 29. In number 2, if we try to plug negative 1 into this function, we get negative 1 plus 1, which is 0 in the denominator, and we can never divide by 0. So we have a problem. We have 0 in the denominator, and we're going to try to eliminate the problem so that we can eventually just plug negative 1 in. Well, in this case, we have the limit as x approaches negative 1 of, well, we can factor the top. And it factors into, let's see, 2x and x. I think I need a negative 3 here and a plus 1 there. And I get 2x on the outside and negative 3x on the inside. That's going to give me that negative 1 that we want. Now that's over x plus 1. Now that we have x plus 1 on the top and x plus 1 on the bottom, we can cancel those out. And now we just have the limit as x approaches negative 1 of just simply 2x minus 3, which is 2 times negative 1 minus 3, which is negative 2 minus 3, and finally negative 5. If we look at number 3, we have the same issue. We have 0 in the denominator if we would plug 0 in for c. Now, if you look at this, it's a complex fraction, so we're going to just simply get rid of the complex fraction. And we're going to multiply everything by the little common denominator, which is 4 and c plus 4. And we're going to use this really 3 times. And we can't forget to have 4 and c plus 4 in the denominator as well. So when we multiply the top left, the c plus 4's will cancel out, and we're just left with 4. So we have the limit as c approaches 0 of 4. On the top right hand, the 4's are going to cancel, and we're left with c plus 4, but we have a minus in the middle, so we want to be careful and leave the parentheses in. Now on the bottom, nothing cancels out. We have 4c times c plus 4. Well, now we have on top 4 minus 4. That's going to give you 0. So we have the limit as c approaches 0 of negative c over 4c times c plus 4, which is equal to the limit as c approaches 0 of, well, the c's are going to cancel out. So we have negative 1 over 4 times c plus 4. And finally, we can plug 0 in for c. We don't need the limit anymore. So we have negative 1 over 4 times 0 plus 4, which is negative 1/16. And there's your final answer for number 3. In number 4, we still have 0 in the denominator. Now we cannot cancel these x's, of course. You can't cancel part of an addition problem on top or on bottom for that matter. So we can't get rid of the problem. We can't get rid of the issue that we have 0 in the denominator. So this one just simply has no limit for now. On number 5, we have the square root of x minus 1, and of course the limit as x approaches negative 3. But if we look at the graph of this square root, just the square root of x, looks something like that. And the square root of x minus 1, if we plug a minus 1 on the inside, then that moves it to the left 1. So there is no possible way we can find the limit as x approaches negative 3 because this function never gets to negative 3, so this one has no limit for sure because it just doesn't exist there. Number 6, we have the limit as x approaches 0 of 3 plus x to the third minus 27 over x. Well, again, we have a problem that we have division by 0, so we need to get rid of that problem. And we can do this by expanding the 3 plus x to the third. So let's just do that kind of off to the side here. We have 3 plus x, and 3 plus x. There is a quicker way to do this, but I'll do it the long way. 9 plus 6x plus x squared, and we have 3 plus x. We'll distribute the 3 through, 27 plus 18x plus 3x squared, and now we'll distribute the x through. We have 9x plus 6x squared plus x to the third. Now we combine like terms, and we have the limit as x approaches 0 of 27 plus 27x plus 9x squared plus x to the third. And of course, we're going to bring the minus 27 down with it, and this is all over x. Our next step in this problem is noticing that the 27s are going to cancel. 27 minus 27 is 0. That goes away, and what's left can be divided by x. So we have an x squared, and x to the third divided by x. So we can write this as the limit as x approaches 0 of 27 plus 9x plus x squared. No more denominator because we divided by x. Now I can plug 0 in with no problem at all. As a matter of fact, this becomes a fairly straightforward problem. 9 times 0, I'll write it all out. 0 squared, and that finally equals 27. So the limit of the original is also 27. Even though there's no value at 0, it has a limit at 0. We're going to talk about a very important limit. As you can see, we have the limit as x approaches 0 of sine x over x, and it is equal to 1. Off to the side here, we have the graph of this function, and the graphs don't show holes in the graph very well, but there is a hole right there at the point 0, 1. Even though there's a hole there, we can still have a limit there. So the limit is 1, and you are asked to memorize this, because we can use this to find the limits of other functions for the example, for example, the problem we have below here. The limit as x approaches 0 of the tangent of x over x. I can write this as the limit as x approaches 0 of sine of x over cosine of x. That's one of the techniques that you talked about in your pre-calc class when you proved identities. One of the techniques was to change everything to sines and cosines. Well, in this case now, we can multiply the top and the bottom by cosine x because this is a complex fraction. And now this is the limit as x approaches 0 of sine of x over x cosine of x, because these cosines will cancel. Now we can split this up into two limits. The limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. Now you've been asked to memorize this one right here. This one goes to 1. So we have 1 times the limit. Well, we don't really need that now. So we have the limit as x approaches 0 of 1 over cosine of x, which becomes now 1 over cosine of 0, which is 1 over 1, which is 1. So the final answer in all of this ends up being 1. But the point is, we used this identity to finish the problem that we were given. Let's talk about left and right-handed limits. Take a look at f of x. It has one line segment going to an open dot, another line segment going to a closed dot. Notice that we have this value, this function value right here. So there is what's called a removable discontinuity. We'll talk about that later in the year. But for right now, we just want to find out what functions are doing from the left and the right hand sides of a value. We have the first problem off to the left here. Limit as x approaches -1 of f of x. So we want to see what the function is doing to the left of -1, and we can see that the limit is actually approaching a value of 2. Right here, a value of 2. So this is 2. The next problem says, what is the function value for -1? In other words, what is f of -1? Well, the function value at -1 is down here at -1. The next one says the limit as x approaches 2 of the function. Now, this is from both sides. So here we are approaching 2 from the left, approaching 2 from the right, and the value is actually 2. The limit as x approaches 3 of this function. Here we are approaching a value of 3 from the left, and in order to have a limit at a point, not left, not right, but just at a point, the left and the right hand limit must be exactly the same. So in this case, the limit does not exist. The left hand limit is up here at 1, 2, 3, 4, 5, 6, and the right hand limit is down here at 2. So there is no limit at 3. Now the limit as x approaches 3 from the right, that one does exist. Here we are coming from the right, and the value is 2. The limit as x approaches 3 from the left of f of x, we've already talked about a little bit, is 1, 2, 3, 4, 5, 6. Here it is approaching from the left, the value is 6. Now even though there's an open dot up there, that means it doesn't have a function value up at 6, but the limit still exists there. In the last one here, I believe it is the last one, yes it is, the limit as x approaches 4 of f of x and then plus 3 can be split up into the limit as x approaches 4 of f of x plus the limit as x approaches 4 of just 3. Now the right hand side, the limit as x approaches 4 of 3 is just simply 3. So what we want to find out is what's the limit as x approaches 4 of f of x, and then we can just add 3 to that. So the limit as x approaches 4, in this case 1, 2, 3, 4 is a value of 1. So we simply have 1 plus 3. Final answer is 4. This is number 52 right out of section 2.1. It is a piecewise function. It says f of x equals 3 minus x when x is less than 2, 2 when it's equal to 2, and x over 2 when x is greater than 2. The question is, what is the limit as x approaches 2 from the right? So let's draw a little graph of this just to see what's going on. And our interesting spot is at 2. To the left of 2, well, let's plug in 2 on the top. We have 3 minus 2, that's 1. So we have a value of 1, and that's an open dot because it's not equal to. And on the left-hand side of 2, we have a slope of negative 1. So we need to go up 1 and left 1. So there's to the left of 2, very roughly. Right at 2, we have a value of 2. So there's the function value at 2. And on the right side of 2, we actually have a slope of 1/2. So we would go up 1 and right 2, and there's to the right of 2. Now the question is, what is the limit as x approaches 2 from the right? And the answer now is 1. Because as we approach 2 from the right, we're getting closer and closer to a y value of 1.